Hi, hello, hi. This is the second part of lesson 3. This is on bond energy. This will be pretty quick compared to the Lewis structures one. It's a lot less, a lot fewer examples to go over here. So we already talked about lattice energy in lesson 2. And lattice energy is the amount of energy released when an ionic bond is formed. Okay, so we have, atoms, ionization energy would be removing an electron from a metal. Electron affinity would be pulling an electron towards a nonmetal. And then we have the energy released when the bond is formed between the two. And that will give you your lattice energy. And that's dependent upon ionic radius as well as the charge differential between the ions. What we haven't talked about is the energy involved in covalent bonding. So when we have covalent bonds form, we form these discrete molecules versus these large networks of crystals like ionic bonds form. So we can calculate the amount of energy involved in the during the process of a chemical reaction involving covalent substances. Now, bond energies or bond enthalpies, whatever you want to call them, can be found in the appendix of any chemistry textbook, just like we would find delta G values and heats of formation and standard entropy values in an appendix. These would be values that would be given to you. What you need to remember is the concept of BARF. When I break bonds, energy is absorbed, and when I form bonds, energy is released. So make sure you understand that. Overall, bond enthalpies are going to be positive values because it's really when you're given this like chart over here, it's the amount of energy needed to break that particular bond. So when you want to calculate the overall energy involved in a process, so a delta H for an overall reaction, it's another summation. This is not on the reference sheet, so you have to memorize how to do this. So all it really is the sum of all the bonds that you're breaking minus the sum of all the bonds that you're forming. So it's broken minus formed. I can't. Oh, please help. Break minus form. So think of it in terms of reading the chemical reaction. You would read a chemical reaction from left to right. Your reactants are the ones that you're breaking apart. Your products are the ones that you're forming. And you just have to know to subtract those values. These are average bond enthalpies because this, you don't have to know this, but when you're talking about a carbon-hydrogen bond, for example, the energy involved in breaking a carbon-hydrogen bond in a methane molecule is different than breaking the energy involved in breaking a carbon-hydrogen bond in chloroform. You don't have to know that, though. I also want you to keep in mind differences in bond enthalpies between single, double, and triple bonds, because that would be data that's given to you. So you have to be careful. Which you'd be given like a little truncated version of these charts, right? You'd be given the energies for certain bonds that you need for the reaction they're questioning you about. But if you look at the difference in these bond enthalpies for a single carbon, double carbon bond, or triple carbon bond, the bond enthalpy for a triple bond is much higher than the bond enthalpy for a single bond. So that must tell you that it's stronger. Okay, the more bonds you have, the stronger it's going to be and the harder it's going to be to break. So let me show you an example of how you would calculate this. So you'd be given, you'd be given a list of values here. You don't have to memorize these. You just have to know how to put them together. So I have it written out in red here, but I want to show you where these numbers come from. I would recommend, these are going to be simple molecules. You're going to be asked to, simple processes. This could show up as a multiple choice question. Oh, you're not going to have multiple choice. Anyway, oh my goodness, this world is on fire. If you were given a multiple choice question, it would be like a simpler version of this, just because this would be tedious with all the different math you'd have to do. But the idea here is sketch out the molecules that are involved here. Include like multiples based on coefficients. Here's HF. Okay, there's H's here. Just so you can see how many are involved here. So let me change color. So you would need to break 1, 2, 3, 4 CH bonds. That's this here. So 4 times 4, 13, because I'm breaking 4 of those bonds. You would also need to break 2 chlorine to chlorine bonds. There's the 2 times 2, 42. You would need to break 2 fluorine to fluorine bonds. That's the 2 times 155. Okay, and now we're looking at the product side. So this is all of our reactants, all of the bonds that we have to break, we would add together. Careful with your calculator work on these problems. They're easy to set up. Write down your full numerical setup. I would take the time to just do in each individual, multiplication section first, then add them all together just to simplify it for yourself. And then for the formation part, I'm making 2 carbon to chlorine bonds, which I don't know if this one's it or not, but let's pretend. And I'm making 2 carbon to fluorine bonds. I'm also making 2 hydrogen to fluorine bonds, and I'm making 2 hydrogen to chlorine bonds. So I would add all that stuff together. That gives me the overall delta H for the reactions. This is yet another way of calculating delta H. Here's another example, and this would be like a more likely scenario. You'd get this little short version of it. So this molecule here, CH3N with this triple bonded C, this is how it would look. CH3N triple bond to another carbon, and then I want to make CH3C triple bonded to a nitrogen. Okay, so all we're really doing here is we're taking this little section and we're gonna reverse it so the carbon gets attached. So what are we breaking? We're breaking a carbon to nitrogen bond, and we're forming a carbon to carbon bond. Okay, we're not touching anything else here, but they're giving you this extra information. So breaking a carbon to nitrogen, so that's a 305, minus what I'm forming. What am I forming? A carbon to carbon, 347. So that gives me a negative 42 kilojoules per mole. Bond length is also something that would change based on bond energy. Again, these are not numbers you'd have to memorize, but you can see here a single, double, triple bond. The more bonds you have, the shorter they're going to get, and the stronger they're going to be. So you should understand the relationship between a stronger bond being a shorter bond length as well. And that's it for bond energy. There's some practice problems for you to work on in the worksheets.